All right, looks like I didn't clear enough space on my phone, and once again ran out of space in the last video, so that's why it cut off abruptly. I just cleared way more space off, so I think we should be good now. We were in the middle of this example before that video cut out, and I just finished this table here. So the goal is to make a phase portrait for this autonomous DE right here, and to classify these three critical points that we found as asymptotically stable, unstable, or semi-stable. So I'm going to use my table here to complete my phase portrait. On this first interval, we have a positive dy dx, which means we are increasing. On this next interval, we have a negative dy dx, so we are decreasing there. Next interval, I have a positive derivative. It's increasing there. And then on my 2 to infinity interval, positive derivative, so it's increasing there. Okay, now let's look at each one of our critical points. Starting with this one down here, -1. I don't need to graph this on a two-dimensional plane to see what kind of critical number we're looking at, because my phase portrait, whether I'm below or above that critical point of -1, it's indicating that the solution curves will approach that critical point. You can see I'm approaching from here and I'm approaching from here. They're both kind of closing in on that -1 there. So that means -1 is stable. We can just say stable as opposed to asymptotically stable. We understand it to mean the same thing. What about 0? Is 0 stable, unstable, or semi-stable? Well, whether I'm above or below that critical number of 0, I can see that my solution curves will be moving away from that critical point. So that makes 0 unstable. Okay, now at my final critical point 2, below that number, I could see that a solution curve would approach that critical point, but above 2, we're moving away from it, and that's what makes 2 semi-stable. Okay, so that wraps that example up. All right, just a little bit left to cover here. So because an autonomous equation only depends on that y, or that dependent variable, and because x is not playing a role in that, if we were to create a slope field for an autonomous DE, we would notice something very interesting. We would notice that along any horizontal line in the plane, all of the lineal elements will have the same slope. So we've highlighted that here. You can see along this horizontal strip, along this horizontal line, all of these lineal elements are all pointing the same direction. They all have the same slope. And the reason for that is because the points that we would have used to find those slopes by plugging them into our DE all would have had the same y coordinate. Even though they all have different x coordinates, that doesn't matter because we don't use that x when evaluating those slopes. And so that's an important characteristic of an autonomous equation. Now, the slopes along a vertical line can vary, because slopes along a vertical line have the same x coordinate but different y coordinates. And so in those cases, you would be plugging different numbers into your DE to evaluate those slopes. But that horizontal line there, that's an important thing to notice about autonomous equations. And that actually leads to this last topic in this section, which is what we call the translation property. So this property basically says that if you have an autonomous differential equation, and let's suppose that you've found one solution to that, y equals g of x, let's say. If you were to take that function and translate it horizontally, any number of units, either to the right or to the left, then the resulting function will be yet another solution to that DE. So graphically, we're seeing that happen here. For example, this blue curve, if this is the solution curve corresponding to y equals g of x, if I were to shift that curve to the right without stretching or compressing or doing any other kind of transformations on it, then the solution curve given there will correspond to another solution for that differential equation. And it happens that way because of that observation we just made on the previous page. Notice the slopes along any horizontal line in this slope field they all have the same slope. Sorry, the lineal elements along any horizontal line all have the same slope. And so that's going to generate the same curve if we just translate it left to right. We can actually say a little bit more than that, though. And we'll verify this with an example. But let's suppose that, again, we have some dE, and we found one solution, y equals g of x. But let's suppose this is not just a solution to the dE. Let's suppose it's a solution to an IVP, specifically something of this form. dy dx equals f of y, and the initial condition is y of 0 equals y naught. Okay? So if we were to shift this function k units either to the right or to the left, depending on the sign of k here, then the resulting function will be a solution to a related IVP. Same differential equation, and the initial condition this time uses the k that we used as a translation term here. So this constant k will shift this function horizontally either to the right or to the left, depending on whether k is positive or negative, and that k is now used as the input. Same output as before. So let's illustrate that with an example, and then we'll be done with this section. So returning to one of our applications from section 1.3, the population growth model. So the solution to the population growth model given here, it's dp dt equals 1/2 p with an initial condition of p of 0 equals 100. Remember what this means? This is the differential equation that governs the growth of that population, and this is the population at time 0, 100 members of that population. We can verify by just plugging it in, it's very easy, that this p equals 100e to the t over 2 power is a solution to this IVP, right? You would check the initial condition by plugging 0 in for t to see that we do in fact get 100 as our output, and then, substitute this into the dE to make sure it works. What I would like to do is take a look at a related IVP and find a related solution using this translation property. So again, what we want to do is show that the solution to this IVP, which compare it to this, the only difference is that the input here is a 60 as opposed to a 0. Everything else is the same. Our translation property says that the solution to this IVP should be the same as this IVP, but shifted 60 units to the right. Or in other words, change that t into a t minus 60. We just want to verify that actually does work in this case. So to show that this is a solution, what I would do is first check the initial condition by plugging it in. P of 60 is equal to 100 e to the 60 minus 60 over 2. Of course, 60 minus 60 is 0, so this is e to the power of 0, which is just 1. 100 times 1 is just 100. That's what we were expecting to get from our initial condition here. Now I need to check my differential equation. So I need dp dt in order to check that. If this is what p is equal to, then how do we find dp dt? Okay, it's not a difficult derivative to take. In fact, the derivative of this would just equal 1/2 times 100 e to the t minus 60 over 2. And of course, I could multiply that 1/2 in and get 50 e to the t minus 60 over 2. However, notice that this is the same thing as 1/2 p, because the thing inside parentheses here is how we defined p in the first place. So we have verified with very little need for a lot of work that this actually does what it claims to do. So that's verifying that translation property for this population growth model. And that's going to wrap up section 2.1.